Welcome to this movie on advanced statistical mechanics, which is the name of a course I teach for master students at the University of Delft, the Technical University. I'm Jos Thijssen, and in this movie I want to explain about the flow of the configurations of a system through phasespace, and an important theorem in that context is Liouville's theorem. So that is the subject of this movie. I hope it's a useful movie. If you consider a macroscopic system, you note that it consists of many particles. All these particles have degrees of freedom, and in general we are not interested in the details of those degrees of freedom. For example, if I have a glass of water, I am interested in its volume and in its temperature, but not really where the atoms in that glass are and how fast they are moving. However, we would like to understand the thermodynamics of macroscopic systems from the details, so from the behavior of the particles on the microscopic scale. And so, if we want to establish that relation, we should first look at which are these states that the system can assume, the states the system can be in, if we would give a full description of the system. So we have a set of particles, I runs from I to n, and in classical mechanics the state of the system is fully specified by giving all the momenta and all the positions of the particles. In quantum mechanics, however, the system would be described by a wave function, and that wave function is extremely complicated for so many particles. Well, we are not interested in the details of those states. However, we would like to know the behavior and the relation between some intrinsic and extrinsic variables, and those are usually only a handful, as opposed to 10 to the 24th typically of the microscopic degrees of freedom. And so the relation between the two is established by this fundamental principle of statistical mechanics, which says that the entropy, that's S, is related to the number of states accessible to a system. So that's omega. So if the system can access a certain number of states, omega, then the entropy can be calculated from this simple formula. Well, one puzzle is the fact that classical mechanics is time reversible, whereas the entropy always grows. And in order to get more insight into that, it's useful to look at the flow in phasespace. So what is phasespace? Well, we have seen that the microscopic state of a system is given by all the momenta and all the positions of the particle. And so if we have n particles, we have 3n momenta, 3n position, well, we have n momenta, but 3n momentum components, we have 3n position components, and so we need 6n degrees of freedom to fully specify the system. And so the phasespace, which is a 3n dimensional vector of position, so that's q to the power 3n, that's just all the positions of the particles, and these are all the momenta of the particles, also 3n components. It's not to the power 3n, but just 3n components. So in total we have a 6n dimensional space, and that space is called the phasespace. So if we have a state of the system, so a particular value for each of the positions of the particles and each of the momenta, then that corresponds to one point in this 6n dimensional space. And what I've drawn here is only a two-dimensional cartoon of the phasespace. And the change of the system is governed by the Hamilton equations, which I have repeated here. So q dot j alpha, the velocity of the particles, is dh dp ja, and we have the change in momentum, and that is given by well, if it's conservative force in the Hamiltonian, then this is just Newton's second law, which says that the rate of change of the momentum is related to the force on the particle. I've used a notation where J labels the particles, runs from 1 to n, and alpha is a Cartesian component, so that is either x, y, or z. And so these two equations are first order equation, and that means that I just need to know where the system is at time t is 0, so suppose it's here. Then these equations tell me how this point evolves. And so in most cases this evolution is unique. Once I know the starting condition, I know all the q's and the p's, then these equations have a unique solution and they define a unique trajectory. Only in some unstable points it may be that there are more points emanating from one original point, so you may go this way or that way. For example, when you put a little ball on the top of a hill, you don't know in which direction it will fall, but in general those points are extremely rare, and so we will assume that every point has a unique trajectory passing through it, so trajectories cannot cross. And so if we have another red point here, there is a red trajectory coming out of that, and it will evolve also in time. Now it is impossible to introduce the entropy without a notion of uncertainty. So we assume that we can only give the position of particles, that we can measure the positions and the velocities of the particles with a finite uncertainty, and that is indicated here by the red box. So we cannot distinguish in this case between the black point or the red point, because they are both in a very small box which defines our resolution with which we can measure. And so what will happen to all the particles in the box? Well, typically for a gas of interacting particles, these curves, they will diverge. So one curve will go this way, the other curve will go that way. Another point, for example a green point, may go this way. And so we see that this original region, this small rectangle here, so it would be a small 6n dimensional block in the real phase space. When we consider all the points and we follow them in time, then after some time they will go everywhere. They will go all over the place in phase space. Now if we consider all the points forming this little rectangle, so in real phase space it's a small 6n dimensional volume, then we see that in the course of time this rectangle will certainly change its shape and probably also its size. So what would happen? Well, in view of the fact that all these points are going all over the place, we would be tempted to say that the size, so the volume of this small initial volume, will grow in the course of time. On the other hand, that seems to be in contradiction with reversibility of classical mechanics, which says that if I then would reverse the time, go back in time, that the volume would shrink again. So that would suggest that there is no preferred direction for that volume to go in the course of time. So now we shall analyze this more thoroughly by looking at the volume in phase space. And so here is my little cartoon of a small volume. It's called omega, and I'm integrate in phase space over all the 6n coordinates over this region omega. And we do that, well, obviously this omega will change its shape in the course of time. So after some time it will perhaps have this form. So that's my omega t, and this is my omega 0. And what we would like to know is how the volume that we calculate in this way, how that changes in time. And in order to do that, we take t small and positive, and we compare that with t is 0. So we go from time t is 0 to a small time greater than 0. That means that we go from the initial positions and momenta to final positions and momenta, we keep this time, this small time, fixed, and then we note that the final momenta and positions depend obviously on the initial momenta and positions, so we can write the final positions as a function of the initial momenta and positions, and the final momenta also as a function of the initial momenta and position. And so we can view this as a mapping, so we go from the initial points x to final points y, so we map the points x in a time t to the points y. And if we have an integral over an area which changes according to this mapping, then we know from mathematics how we should deal with that, because the integral of the new volume, so of the mapped volume, is related to the original integral via a so-called Jacobian J of the mapping. That's the matrix, this Jacobian, and it's defined as the dyi, then take the derivative with respect to dxj. So that is what mathematics tells us. It's not this matrix which directly gives us the transformation, but it's the determinant of that matrix, and this is often called the Jacobian determinant. So what we need to find is this Jacobian determinant for the mapping which brings us from t is 0 to t is t, which is a small fixed time. And now we use the factor t is small so that we can really explicitly make this mapping. So we go from qj alpha at time 0 to qj alpha at some later time, and that is related of course by the derivative, so t times the derivative q dot, but q dot can be written as dh dpga alpha due to Hamilton's equation of motion. So the qj dot is this derivative here. Similar for the p dot. The p dot is given by this derivative here. And so we see that if we take the p's and we take the derivative with respect to the p's, I've divided up the matrix here in the p part and the q part along the horizontal and the vertical direction. And so here are the p derivatives of the p's. So I take this pj alpha t and take the derivative with respect to a delta pk beta. Then first I get a derivative from this one, which is just a delta function. The j alpha alpha should be the same, so that gives me a unit matrix in this block. And from this, when I take the derivative with respect to dbk beta, I get a double derivative of h with respect to the q and with respect to the p. Now if I take the q and I take the derivative with respect to the p's, I can only, of course I don't get any contribution from this term because that doesn't depend on the p's. The q's and the p's are independent. And here I get a double derivative of the h with respect to two p's. When I go to the p and I take the derivative with respect to the qj, I can only also get a contribution from this term, which is a double derivative with respect to the q's. And if I take the derivative of qj alpha with respect to qk beta, then I get this form, which is very much like that one. Now let us see what we get. Now we are going to write this as an expansion in terms of t, and so the terms which do not have any t, they can only come from the unit matrices here and the unit matrix there. So we take 1 times 1 times 1, etc., etc., so that gives me a 1. Now I can of course also pick one of these terms, but as you can see, for each of these terms I find the same term here but with a different sign. So if all the terms that are linear in t, by taking here just the t, are cancelled by a term also of order t, which occurs in the lower right block of the matrix. And so the determinant of j is 1. First, we don't see any way to get a contribution proportional to t by picking one of these. So suppose I would take here an off-diagonal element. That also doesn't help, because then I have to take also an off-diagonal element somewhere else, and then I get a contribution of order t squared. And it's the same when I take, for example, a 1 here. I take one element there. As soon as I take an element there, I also need an element there. They are both proportional to t, so everything is proportional to t squared. So what we can say now is that the vt is equal to the vt is 0 plus something which scales like the order of t squared. And from that we can conclude that the derivative of v with respect to t is 0. And that means that the volume remains constant. So how would you do that for longer times? Then you just integrate up the derivative from 0 to t. And we know that the derivative everywhere using this analysis can be seen to vanish. And so everywhere this gives me 0, and I have to add, of course, the initial volume, and you see that the volume in phase space doesn't change. Now that leaves that leaves a puzzle for us, because we know that the entropy changes, and the entropy is the number of states that are available to the system. So suppose we start with our little red block again. Then the entropy is a kind of measure for the number of points in this block. Now there are infinitely many points in that block, obviously, but we can still count them provided we just look at the measurement accuracy. So that means we take this initial volume, that's this oval here, and we have all these small cells which tell us which two states we can really distinguish, and then the number of distinguishable states, they are proportional to the surface area inside this oval. So it's the volume inside the oval. Now this shape here, let me move it a little bit. So this shape on the right hand side, that's what I get after some time t. And you see that it's a very slender, very narrow, very dendritic structure. It's everywhere very narrow, and it covers a large surface area. That means that if I would like to cover this complicated shape with blocks, little blocks similar to the ones used there, I need many more. So you can count the blocks here, but there are about 1.5 times as many as you have here. So although the surface area inside the volume has not changed, when it really becomes a kind of dendritic structure, I need more and more blocks in order to cover it. And so if I count the entropy, if I look at the entropy, that increases because the number of states here, that's the number of blocks I need to cover this shape, that increases. And so usually we take for this little volume, we take the smallest size that is allowed for by quantum mechanics. So if I have P here in the vertical direction and I have Q in the horizontal direction, then this little block gives me a delta P times delta Q, and Heisenberg uncertainty relation suggests that we should take therefore a value which is larger than Planck's constant, and we can write that also as 2 pi times h bar. And so we have seen that although Liouville's theorem tells me that the initial volume will always be preserved, so it will not change in the course of time, that the entropy can still increase, but it depends. Obviously that depends on the way I count different states, and in this case I need a certain amount of uncertainty in P and in Q in order to define the entropy properly. And so entropy cannot be defined if I do not include any type of uncertainty into the system, and the uncertainty is here defined by the size of these small blocks. So we have seen that the initial volume which is occupied in phase space will not change its volume in the course of time. Now there is another way to analyze the flow in phase space, and that's also called Liouville's theorem. And in fact this is based on the fact that there are no trajectories that suddenly start from nowhere. So we have initial states, and they will always remain, they will not disappear, and we will have no new trajectories. There will not be spontaneous occurrence of new trajectories, of new system configurations. Both are of course extremely obvious assumptions, and we can use those in order to describe the behavior of the density of points in phase space. So sometime we can, in some region of phase space, we can have many points, so then there is a high density, or there can be only very few points. There is a low density, and as usual we define this density according to the following rule. Take the density rho as a function of all the momenta and the positions, multiply it by a small volume element in phase space, and then count the number of points within that small area. So if you look at this picture here where we count by just counting boxes, then we assume that this volume element is a lot larger than these boxes. So it's still small in comparison to the scale over which the rho varies, but the little boxes are much smaller than this volume. So it's large with respect to the measurement boxes. And if there are no sources and no sinks, and rho is a density, then we know that it should always satisfy the continuity equation. And the continuity equation tells you that a change in rho is given by minus the divergence of the flow of the flux. And so what this says is that if I look in a little box, and I look at the change of the density inside that box, that change is caused by trajectories moving in and moving out. And if there is an imbalance between the trajectories moving in and moving out, there is indeed a change in that rho. And so the change in the rho should be caused by all these differences of the flux, for example, through the left face and the flux outside the right face. If they are equal, then this gives a zero contribution here. If they are unequal, they give a non-zero contribution, and that should be precisely the increase or the decrease of rho inside the box. That's the continuity equation, and we know that for such a density field, the J, the current density, is given by rho, the density of points, times the velocity. And in our case, the velocity is simply given by the time derivative of the points. So it's the time derivative of the 6 n-dimensional vector in phase space. That's the velocity, as usual. And in our case, that's p dot, a 3 n-dimensional vector, and it's q dot, which is also a 3 n-dimensional vector. So we know what rho is, we know what J is. Now we need to formulate the derivative. The derivative is the gradient in phase space. It has 3 n components corresponding to the derivatives with respect to the p, g, alpha, and 3 n derivatives with respect to the q, j, alpha. So it's a 6 n-dimensional gradient, as it should be. And if we would write it out, we would get a very long list of d dp1x, d dp1y, etc. up to this, and then you have d dq1x, 1x, d dq1y, etc. So we can put that now into the continuity equation. Left hand side is simply d rho dt, partial derivative, And the right hand side is this gradient operator. So here we have the first ones. There is always a minus sign in the continuity equation. And here we put a j, which is rho times first the p dot j alpha, and the derivative with respect to the q j alpha acts on the j corresponding to the q dot j alpha. So this is my equation, and here I see always a derivative and then a product. So I use the product rule, where I first look at the derivative of d rho dpj alpha, and then for this term the p dot j alpha, that is minus dh dq j alpha. So this minus sign here disappears. So here I have repeated the Hamilton equation, so we can replace this by minus dh dq j alpha. Then the second term is just rho extracted in front of the derivative, and then I take this expression for the p dot with the minus sign, and I take the additional derivative with respect to dpj alpha. So I have now a double derivative. I have a d squared h dq j alpha dp j alpha. Now let's move on to this term. So here was a minus sign, and this term, this q dot j alpha, can be replaced by dh dp j alpha, and that directly gives me these two terms. And now we note that the second term is the same as the last term, but they have opposite signs, so they cancel each other. And what I'm left with is this expression, and we use a special notation for that. That's bracket brace, in fact brace rho comma h. So in general, these brackets, these braces, are defined as for f and g, both depending on all the q's and the p's, as df dq dj dg dp minus df dp dg dq. And the name by which this symbolic notation goes is the Poisson bracket. So if we have a brace and then two quantities depending both on the p's and the q's and a comma in between, then it means this full expression, and it's called the Poisson bracket. So some properties of the Poisson bracket. First of all, you can see from its definition that if I would swap rho and h, this term would turn into that one and that term into this one, and because of the minus sign separating the two, we can immediately see that you get a minus sign once you swap the two. Furthermore, if we take two of the same objects, you can see that here, suppose that g would be the same as f, you can see that this term is the same as this one but with a minus sign, and so any Poisson bracket of two identical functions is 0. And in fact it's not difficult to see, it's a good exercise to check this. If I take any function of a function a, which in turn depends on the q's and the p's, and I take the Poisson bracket with h itself, that also vanishes. And so that gives us a very good candidate for this rho. So at equilibrium, what we would like to have is that the density inside the box doesn't change. So if we wait really long, so we prepare a system and it's really far from equilibrium, and we wait a very long time, if we wait long enough, the system will reach equilibrium, and in equilibrium we expect that there's no change in the configurations that are visited by the system, and therefore we impose d rho dt equals 0. And one way to, that implies that the rho comma h, the Poisson bracket, is 0, and a good way to realize that is to take for rho any function of h. And so a particular function that we could take is the delta function, where we say okay, rho is the delta function of h minus e, which means that only those p's and q's are allowed for which the Hamiltonian has a fixed value E. So E is a fixed parameter, and that's the energy. Now this is called the microcanonical ensemble. So it corresponds to an isolated system which conserves its energy, so the energy stays constant, and the volume and the number of particles is also constant. Now another famous option is to take for rho minus e to the power minus h over kBt. That's recognized as the Boltzmann factor. We need some normalization constant. We will come back to that in a later movie. And this is the famous canonical ensemble. So, what we have seen is that Liouville's theorem gives you insight in the relation between the microscopic details of the system and the probabilities. And these probabilities, they can be related to the entropy. And so that provides mainly the link between statistical mechanics and thermodynamics.